right, so here's the next step in our little lesson here about oxidation reactions, or redox reactions. In order to be able to take a look at balancing redox reactions, we have to be able to assign oxidation charges. So if you take a look at these little pictures that I have up here on the screen, you can kind of see some different compounds made from real similar chemicals, but their oxidation states are different. For example, this one over here is copper compounds. The one in the middle here is iron. We've got chromium, manganese, iron, cobalt. Over here, these are all plutonium, or platinum, what am I saying? Plutonium. Anyways, different charges of them. It's been a long morning. These different charges, not just for pretty, not just for making chemistry annoying, but they actually do have some very different ways that these elements will react, these ions will react depending on what their charges are. So again, it's something that we do have to kind of deal with on a more than just a theoretical level, but that's all right. You have done some of this redox stuff before. In order to identify redox reactions, you have to know that a charge has changed. Well, in order to know if a charge has changed, you got to be able to know what the charges are, duh. So there's a couple of basic vocabulary things here that you got to get. Number one, this phrase oxidation number or oxidation state, they're kind of reversible. This is what we're going to call the charge. It's the apparent charge of an element. It turns out that certain things, if we want to be really, really picky, certain things when they're in compounds actually have charges, like ions. They actually have a +1 or a -1 charge. And then certain things kind of act like they have charges, more of those covalent types of compounds. They don't really have a charge. They're just sort of apparently acting like they have a charge. So the word oxidation number is more technically correct. But again, in your head, if you want to think about what the charge is, whether it's +2 or -2, that's going to be close enough for most of what we do, except for that vocabulary question on the test. A couple basic rules here. Number one, we've already used these, but elements have an oxidation state or a charge of 0. They're neutral, that's why they're atoms. Even diatomic ones, so like oxygen O2, it's still got a charge of 0. Ions, on the other hand, when they're in a compound, we're just going to say the oxidation state's equal to their charge. So magnesium becomes a 2+, oxide becomes a 2-, and those are their oxidation states. So in this case, the oxidation state and charge, same thing. So that's not too bad. But we know that there's a whole class of compounds where trying to figure out what their charge is can be a little bit trickier. We've called those transition metals. Those are the ones where they can have more than one charge depending on, I don't know, the weather. But like copper, for example, can be copper 1 or copper 2, and iron over here, iron 2 or iron 3. And there's a whole bunch of different ones. Almost all of the transition metals have 2, 3, or even 4 or more oxidation states that they can take. So how do we figure out what those are? And that's part of what we're going to deal with in this particular lesson. It's not that hard. We've done it before. But that's why we use Roman numerals. You just can't always tell from a formula. However, what you guys probably don't realize is that nonmetals can also have variable oxidation states. And there's 3 examples here. There's oxygen, nitrogen, and sulfur. All 3 of these, in fact, all the nonmetals. But these are 3 examples of some different combinations that you can get. Now, these aren't actually charges. These are truly oxidation states. Oxygen doesn't truly take the charge. It just pretends. It's kind of a weird thing. Same thing with sulfur. But oxygen oxide, like in water up here, is 2-. But remember, we've dealt with peroxide. It's been a little while. But peroxide is where oxygen acts like it's a 1- charge. So just some differences to it. Nitrogen can combine 1-to-1 with oxygen, or 1-to-2 with oxygen, or 2-to-3 with oxygen. So you can kind of figure out there's some different possible charges that nitrogen can act like. And sulfur, same thing over on the right there. It can be a -2, a 0 when it's in its element form, +4, or even a +6. There's some just different kinds of things that they can act like. And we have to go through some rules to be able to figure out what those charges are. The rules are pretty logical, but they can be kind of a little bit tricky in some spots. So let's take a look at an example of this. How do we assign oxidation numbers? These rules that are on here, 2 that you've already seen and a couple extras, are going to get you right about 80% of the time. And I'll give you the other 2. There's a total of 6. I'll give you the other 2 here in a slide or 2. But it's not that bad. You just have to be able to use a little bit of logic and kind of work backwards from your formulas. Remember, we've joked about crossing up a variety of times with our formulas. That's kind of the process you're going to use here. So rule number 1, elements have a charge of 0. If you ever see an element by itself, it's got to be a 0. If it's an ionic compound, so we're talking about a metal from the first or second column and a non-metal from like the last column, those are going to have the charges kind of like you're used to. Transition metals are a little bit trickier, and non-metal is a little bit trickier. We'll get there on the next slide. Oxygen, for all intents and purposes, oxygen is always a 2 minus. This is only the case, or only case where it's not true is in peroxides. I'm not going to give you that in this real chapter, I don't think. But oxygen, you can pretty much look at that, go 2 minus, and just go from there, and I'll show you why that rule works a lot for us. And then the last bit, we did this when we wrote formulas. Those charges have to add up to 0. So if oxygen's a 2 minus and there's only one copper with it, that copper has to be a 2 plus. So there you go. So over here is a couple of practice problems. I'll run through them on the next slide. So you're going to hit pause here. I've got two forms of copper and oxygen. The black one at the top is CuO, and the rusty colored one at the bottom is Cu2O. So see if you can apply these 4 rules that we've got right here, and see if you can figure out what the apparent charge, the oxidation states are on copper and oxygen. Hit pause, get a scratch piece of paper. On the next slide, I'll be moving forward and showing you how it works. Okay, so here it is. For the purposes of what we're doing here, rules 1 and 2 are not going to really apply because it's not an element present. These aren't really ions because these are transition metals, so we got to kind of do a little bit extra thinking on this. So we're going to start with rule number 3. Rule number 3 is oxygen's a 2 minus. So in copper oxide, oxygen's a 2 minus, and in this copper oxide over here, oxygen's a 2 minus. Now we're going to cross up and use our subscripts to figure out how to make rule number 4 work. And rule number 4 is that the last thing, the total charges have to add up to 0. So in this particular case, if oxygen's a 2 minus and there's only one copper with it, that copper must be a 2 plus for it to add up to 0. In this case, it's a little bit different. There's 2 coppers, so each copper has to have a charge of 1 plus for the total thing to add up to 0. So each copper is a 1 plus. There's 2 of them for a total of 2 plus, and oxide's a 2 minus. Not too bad. Like I said, we've done this before, but it gets a little bit trickier when we're dealing with nonmetals. So moving on. What's my next slide? There it is. These last 2 rules, numbers 5 and 6, these are going to get you the rest of the time, and these are the little bit trickier ones. So rule number 5 deals with non-metal compounds. Type 3s is what we would have called them at the beginning of the year. These are the ones when it's got 2 nonmetals together, and one's acting positive and one's acting negative. The rule here is that the more electronegative element, remember, electronegativity increases as you go to the top right of the periodic table. So usually it's oxygen, it might be fluorine, but generally oxygen is going to be the one that wins. It's given its regular negative charge, and so that's kind of where rule 3 number comes into play. Oxygen's pretty much going to be a 2 minus. Then you kind of do your math backwards to figure out what the charge in that nonmetal has to be to make it add up to 0. So if you take a look here at what's going on in carbon dioxide, I'm going to start with that rule about oxygen being more electronegative, so it's going to be the 2 minus. That means the total charges from the oxygens here is 4 minus. There is 1 copper, so its charge must be 4 plus. And this is the weird case where copper can be a plus or minus. In this case, the oxidation state for copper is 4 plus. Oxidation state for oxygen is 2 minus. Now here's an example over here for you to try. It's N2O5 dinitrogen pentoxide. Take a break, apply this rule, and see if you can figure out what the oxidation numbers are. So hit pause. There you go. So in terms of this one, when we apply this rule, oxygen is going to be the 2 minus. There are 5 oxygens. That gives me a total negative charge of minus 10. There's 2 nitrogens, so I take that minus 10, I divide it by the 2 nitrogens, and I know that each nitrogen now must have an oxidation state of plus 5. Now remember, this plus 5 is its oxidation state, not its typical ionic charge. When you look at the periodic table, you don't look at that and go, yeah, nitrogen, plus 5. Normally we'd think of nitrogen as being a negative 3, but in this case, that's the difference between a charge and an oxidation state. In this case, nitrogen's acting like a plus 5. It's a really bizarre thing, but just get used to kind of doing that backwards math, and you'll figure out how it works. All right, moving on. Here's rule number 6, the last one. If you've got polyatomic ions, like sulfate, the example that I've got right here, this simply means it's kind of in violation of rule, I think it was rule number 4. In this case, the sum of the charges has to add up to the charge of the ion. They don't add up to 0. In this case, for sulfur, we know the total charge has to add up to 2 minus. Now, 2 minus here is not an oxidation state. That's the charge of the whole thing when it's added up. So, applying our rules. Rule number 5, or rule number 3, depending on how you want to look at it, oxygen's more electronegative than sulfur, so it's given its normal charge of 2 minus. There are 4 oxygens, therefore we have a total negative charge of negative 8. Now, we know that the charge of sulfur plus the charge of oxygen has to add up to negative 2. So, sulfur must be 6 plus, because 6 plus and 8 minus equals 2 minus. And that's how we kind of do that reverse math. And sometimes it's just a little bit weird to remember that you sometimes have to add up to not 0. But that's how you deal with polyatomic ions. So there you go. Here are some practice problems for you. Get a scratch piece of paper. You may want to go back and kind of jot down those notes or take a look at them. See if you can assign oxidation states to all of these, to each element in each of the following. So hit pause and you better hit pause. Don't make me think you're not hitting pause. But hit pause, and then I'll come back and go through these each of these step by step. Here we go. All right, welcome back. So, according to oxygen, oxygen is a gas. It is its elemental form. Therefore, its oxidation state is 0, and that's according to rule number 1. Elements always have an oxidation state of 0. All right, PF3, this is a non-metal compound, so we have to use kind of some of our fancier rules here. So, based on these two rules, I start with fluorine because fluorine's more electronegative. It's the one that has the closer to the top right corner, so I give it its usual negative charge, which is -1. And then, because it's a compound, rule number 4, they have to add up to 0. If this is 3- total, 1 each, then that phosphorus has to be a 3+. All right, moving on. This one's got a polyatomic in there. It's kind of got a multiple kind of stuff going on here. It's one of the harder ones on the page. So I'll start with the most electronegative one if you want to, or you can deal with it as being rule number 3 or rule number 5. I don't really care. But oxygen's got its normal charge of 2-, so that means I've got a 6- charge total from these oxygens. Sodium, which is an ion, it's going to be in column number 1. It's ionic form. It's going to be a +1. So there's 2 positive charges, 6- charges. Therefore, this carbon has to be a 4+. And again, I'm doing this kind of by process of elimination. The nonmetals are going to be weird. The transition metals are going to be weird. You leave those for last. Oxygen, you know what it's going to be. Column 1, column 2, you know what they're going to be. The other nonmetals, you kind of fill those in at the end. So there's my rules for that. For ammonium, same kind of idea here. Go with the most electronegative if you want to. This would be nitrogen in this case, top right, is going to be its normal -3 ionic charge. There are 4 hydrogens here. They each have a charge of +1, 3-, and 4+. It adds up to a total of 1+, and so that makes sense. And then the last one, magnesium sulfide. This is a pretty straightforward one. This is basically an ionic type compound, so there you go. Magnesium is a 2+. Sulfur in this case has to be its 2- form to add them up to 0. So there you go. All right. Make sure to ask me in class tomorrow. We can do some practice problems on this as this is kind of sticky for you. But definition-wise, an oxidation state, it's the apparent charge. In some cases, it's the actual charge. Sometimes it's the pretend charge. Transition metals and nonmetals tend to be the tricky ones where we have to apply a little bit more logic to these because they can have more than one oxidation state. You can't just assume that you know what it is. There are 6 basic rules, actually 4 basic and then 2 kind of higher level rules. But if you can remember that elements are 0 and basic ions are their usual charge, that's going to get you most of the time. Oxygen's almost always a 2-. Total charges add up to 0 unless it's an ion, which is rule number 6, in which case it adds up to the ion. And then in nonmetals, you just have to use that kind of logic, kind of the nonmetals and the transition metals. You got to kind of use that reverse logic to figure out what the unknown one is. So there you go. I'll see you in class tomorrow.